My name is Neha Naveen, and I am a rising junior at Cornell University studying CS and AI. And I am an intern at Anode this summer, and I will be presenting about fine tuning for object detection. So, I want to start by talking about the future of CV and one of the biggest challenges of CV. And that is that data sets are extremely large and diverse, meaning a zero shot model would perform poorly given different data. So there are obviously so many data sets out there, extremely large, and have many different images that are completely different to one another. So a zero shot model would obviously perform much poorer given one set of data versus another. And another challenge is that there are various models available, but there is no easy way to train these and test them and then compare their results and choose the best one. So, this is one of the biggest problems that I wanted to highlight, and I will be talking about this during the presentation and how ANO is trying to tackle this. So, I want to start by talking about what fine tuning is. So, fine tuning is the process of taking a pre trained model and adapting it to a specific data set by leveraging learned features to specialize to the task. So, what does this mean? If you look at this image over here, which I won't go into too much detail about, but essentially what this line of code is doing is it's training a model, and each of these lines is kind of like a specific parameter that you can change and adjust so that it's better suited to your data set. So that brings us to what a parameter is. And a parameter is a learnable value that the model adjusts during training to improve its predictions. And weights and biases determine how important each input feature is and introduces offsets to help the model fit data more flexibly. So I'll probably be using these terms, so this is just what these are. So one of the challenges of this problem is balancing precision and flexibility. So what does that mean? On one side, we have flexibility, meaning the model should be flexible enough to learn and adapt to new data without overfitting. And on the other side, we have precision, which means the model should still be precise enough to stay on track and generalize well to new data without missing subtle patterns. So we don't want the model being too fine-tuned so that such that it's memorizing every single detail, but it shouldn't be so fine-tuned that it misses the big picture and the subtle patterns are being too closely focused on and the general pattern is being missed. So that is what this slide is essentially talking about, balancing precision and flexibility. So an example of object detection and the evaluation problem is that traditional evaluating is tedious and ineffective. So, one of the first problems is that finding the perfect model is quite difficult and takes too long. So, this is the time consuming aspect of it. It's also very inefficient because it's hard to find a model that is best tailored to the data set. And lastly, it's repetitive because the process of comparing results requires too much manual labor. So, doing this entire process is extremely tedious, and that is what ANO is aiming to tackle. So, this is how the workflow is supposed to work essentially. So, in the beginning, the user over here asks for a model that gives a very good precision and recall and other metrics. And so that is the goal of what this person is trying to achieve. So it comes to the annual product saying, here is an unannotated data set of 10,000 images of bird's eye views of military aircraft. So, for example, in this case, the user, she is asking for a military aircraft data set, or she's providing this data set, and I'll walk through the process of what the annual product is supposed to do. So first, the user comes to Anna with her data set, which is unlabeled in this case, and she requests a fine tuned model that should predict where an aircraft is and which type of aircraft it is in this particular scenario. So when the user uploads this data set, the annote product is supposed to help with annotations. So here it says the user is able to provide a small number of annotations using the simple annote UI, which the annote product annotates for the rest of the dataset. So this should take care of the very repetitive and tedious process of annotation. Then the next part of the workflow is training. The model then trains on the dataset with fine-tuned layers and hyperparameters specified to the dataset the user has provided. So the annote product should train a specific model on this dataset that the user has provided with fine-tuned layers that are specific to this dataset. So it should be domain specific. That's what makes the product special. Then the annote product should train and test each model the user selects, such as YOLO, grounding dyno, faster RCNN, etc. So the user can specify or just say any model, and the annote product should train multiple of these. And then the cycle will repeat itself. So this training step should repeat itself for each and every model that the user selects. And at the end of the cycle, there should be an option where the annote product will let them view metrics. So metrics such as the map score, the IOU, precision, recall, maybe F1 score for each model are displayed. And annote can come up with a suggestion for the best model that is offered for this particular data set that the user has provided. Or the user can select which model he or she best thinks fits. So first, for this product, we had an early proof of concept in the beginning stages. We were invited by the Navy Blue Tide project and many other projects that we were able to move forward in. And here's an example of a zero shot versus a fine-tuned YOLO model. As you can see here, we have a validation set and test set for both these zero shot and fine-tuned models. And this was done through RoboFlow. And as you can see here, each category on the zero shot has a much lower average precision by class as the fine-tuned model. So this supports, oh, and also by the way, the data set that was used for this example was a underwater imaging data set in line with the Navy Blue Tide project. So as you can see here, oh, sorry, the zero shot model doesn't perform as well as the fine-tuned model. And this is a proof of concept that if you're not tuning your model specifically to your data set, it won't perform as well, as you can see by the zero shot model over here. So here's a snapshot, which is a side-by-side comparison of the zero shot model versus the fine-tuned model. Before any fine-tuning, the predictions are, first of all, they're spotty. It's missing two of the fish in this image. Yes, it's missing two of these fish. And the percentage accuracy are slightly low. It's not completely sure that it's seeing these things properly. On the right side, however, it's much more confident in actually picking up on the specific classes in this image. So this is the fine-tuned YOLO V11, and predictions after training is much, much better. Yeah, so after this proof of concept that is clearly done on just one data set for one model, we expanded to a research paper where we used three different data sets, the F-Air 1M data set, a military aircraft data set, and trash can data set, which are all open source. And we use these data sets And we trained three different models, the YOLO model, Dino, and Faster RCNN, on these three data sets. And we compared zero shot versus fine tuned models in this research paper. So, moving from our proof of concept, we are going into a more formal application of what we're trying to prove. So, in this case, some of these models used variations of the datasets, others used the full dataset, and we primarily used Google Colab for training and testing and model evaluation in this example, and we compared metrics using a custom evaluation script. And here's just a image of our research paper. So a lot of text here, but I'd want to go over YOLO because that is what I worked on. So a little bit about YOLO. It's an object detector, and essentially it divides the image into a grid and predicts bounding boxes and class probabilities, meaning it puts a box over the specific object in the image, and then it also predicts what this is. And there are many variants. That's what the V8, V11 stand for. So some of the variants are V8. I think V15 might be coming out soon, I believe. And these variants use a CNN or convolutional neural network backbone for box regression and classification. And box regression is just predicting bounding boxes. And then classification, again, is class probabilities, classifying each object as a certain thing. So some requirements of YOLO are pretty special. The dataset has to be stored in a particular format, and it should have a training, validation, and testing folder. And each image in the dataset should be split between these three, and you can choose what split you want. And the labels for each of them must be stored in a TXT file for each image. And they should have some things like a class ID, the X and Y coordinates of the center of the image, and the height and the width. So this is how the labels are stored. And then on top of that, there needs to be a YAML file, which is unique to every dataset. And this is where you have to define dataset configuration for training, such as paths, like the path names of where the dataset is stored, the number of classes, the name of each and every class, and things like that. And then lastly, I want to talk about the model weights. After running, you are presented with a best.pt file and a last.pt file. So best is just a checkpoint with the highest validation performance, and last is a final checkpoint from the last epoch of training. So both can be used for inference or for further fine tuning. And ideally, the anode product can allow for an easy download of one of these or both of these for easy deployment. Yes, so the research paper again was a more formal example of training three different models on three different data sets and comparing zero shot versus fine tuned. And as you can see here, the zero shot did not do so well, whereas the fine tuned models did much, much better. Yes. And then once again, this image that I had earlier, this is just an example of the fine-tuned YOLO training step. So now that I've talked about YOLO, this is just an example of a piece of code that shows how it was trained. This was the training step. So as you can see, you can change the epochs, you can change the batch size, the learning rate, the weight decay. You can freeze certain layers, you can scale things and things like that. So these are just some fine tuning methods that were employed in this example. So for future work, um, it would be a first step in integration to create an SDK for object detection. And the goal would be to upload data, train object detection models, make predictions, and evaluate results using supported models. So, right now, the supported models are, as I said, YOLO, Dino, faster RCNN. So, hopefully, this can expand a little bit more. which brings us to integrating CV into the anode product. Right now, the anode product works with text data, so it's mainly NLP. But as you can see in the research paper, the results were promising for fine tuning. So this shows that the anode product would do very well with multimodal capabilities. So also using CV and image data. And so the anode product is already an end-to-end MLOps framework, but this could also integrate CV, and it could, for the entire operation of having a data set of images, training, testing, and evaluating from start to finish, the entire operation could be done on the anode product. And then lastly, easy deployment. So for any companies, for um, any personal projects that people want to use and the anode product for. The anode product can have an easy deployment. So after it's given a suggestion for which is the best model for this particular data set, the user can download this easily using a simple UI and can deploy it for their own work. Thank you so much. And that wraps up my presentation on fine tuning for object detection. Thank you.